Good morning, students. Dear students, in the continuation with the video lectures on motion on a straight line, we had discussed about the various topics. In the previous videos, we had discussed about the stopping distance, reaction time, and various equations regarding the motion of an object we had discussed. Now, today we are going to discuss a very important topic based on which various numericals will be asked in your examination. So, let us start our discussion with the topic, that is relative velocity. Relative velocity. Relative velocity. As the term relative means what? Relative. As we had discussed that rest and motion are relative terms. So, if you are discussing the motion of a particle, then there is the concept of relative term there. If there is a motion, then there is a term relative. Relative. So, if I am saying that motion of a particle, we assume a fixed point relative to which the given particle is in motion. Motion of a particle means a fixed point with respect to which the particle is in motion. A fixed point with respect to which the particle is in motion. If you say water is flowing, or we say wind is blowing, or a man is running. All this means to say that all these things, water is flowing, wind is blowing, man is running with velocity v, then we can say that all these things are in motion with respect to ground. Means they are in motion with respect to ground. Means all these motions are considered to be with respect to ground or earth. Now, if we have to find the velocity of a moving object relative to another moving object, if there is a problem, to find the velocity of a moving object relative to another moving object, velocity of a moving object relative to other moving object. Then here the concept of relative velocity is needed. Relative velocity. Here the concept of relative velocity is needed. Now we will consider a particle P, and with the frame of reference we will try to clear this problem of relative velocity. Look at here. I am drawing a frame. This is the frame S, and this is another frame, that is S dash, and this is particle P. This is the position of particle P. So this is the position of particle R P S dash. This is the position of the particle with frame S dash, and this is the position of frame S dash with S. So this is the position of particle P with respect to S. This is the position. Means there are two frames. There is a frame S, and the position of particle P with frame S is RPS. The position of particle P with frame S dash is RPS dash, and the position of frame S dash with respect to S is RS dash S. So RPS can be written as position of particle with frame S, can be written as, by triangle law of vector addition. We will discuss just after this topic a scalar and vector, and in that we study about the triangle and parallelogram law of vector addition. There you will be going to be clear about this vector addition method. So this is triangle law of vector addition, and RPS dash is equal to RPS dash plus RS dash S by triangle law of vector addition. Now differentiating both sides with the time t. Differentiating position with time, and on differentiating position with time we will get the velocity. S dash S, or you can write it as velocity of particle P with respect to frame S dash is equal to velocity of particle P with respect to frame S minus velocity of frame S dash with respect to S. Means to say that if the velocities of two bodies are known with respect to a common frame, we can find the velocity of one body relative to other. Means you can say that if velocity of two bodies here the particle P and the frame S dash, particle means though two velocities, velocity of the particle and velocity of frame S dash, these two velocities are known to you, with respect to s, with respect to s, then we can find the velocity of one body relative to other. We can find the velocity of one body relative to other. Means you can find the velocity of point P relative to s dash. Both velocity of point P and velocity of frame s dash. The velocity of point P with respect to this frame can be calculated with the velocity of particle P with respect to frame S minus velocity of particle P with respect to S dash. Velocity of frame S dash with respect to S. So difference of these two gives the velocity of particle P with respect to frame S dash. So this is the clear derivation. So from here we can write that if VA and VB be the velocities of two bodies with respect to Earth. VA is the velocity of an object with respect to Earth and VB is the velocity of an object with respect to Earth. Then the velocity of B relative to A. Then the velocity of B relative to A, that is VBA. It can be given as VB minus VA. VB minus VA. This is the concept of relative velocity. Means to say that if there is frame S, there is frame S dash, here there is point P, and if this point P is moving with velocity P with respect to frame S and S dash, and velocity of S dash with respect to S, then and both the velocities are with respect to this common frame S, both the velocities are with respect to this common frame S, then VPS dash, velocity of particle with respect to S dash, can be given as VPS, velocity of, and VSS dash. Means both are moving with respect to this common frame. S dash is also moving with respect to common frame, and P is also moving with respect to this common frame. Then the velocity of this with respect to this is the velocity of this minus velocity of this. This is the concept of relative velocity, and on the basis of this concept we had deduced this relation. If an object is moving with velocity VB with respect to ground, and object B A is moving with VA with respect to ground, then VB minus VA will give the relative velocity of B with respect to S. This is nothing, this is ground with respect to ground. Means if I am writing velocity of B with respect to ground, the velocity of B means velocity of B with respect to ground, velocity of A means velocity of A with respect to ground. So in this way, this is the concept of relative velocity. And to make this concept more clear, we are considering some examples. To make this concept more clear, we are considering some examples. I think students, with these examples, the concept become more clear to you. The concepts being more clear to you. So, take example A. If two bodies are moving along same line, if two bodies are moving along same line in the same direction, with velocities v and vb relative to ground, then velocity of b with respect to a. Since two bodies are moving along same line in the same direction with velocity and velocity b, means both these velocities are with a common frame. This is common frame, this is s dash, this is particle. So we had supposed this is va and this is vb, and both are moving, this is ground. So velocity of b with respect to a, can be given as velocity of b with respect to ground minus velocity of a with respect to ground. Velocity of a, I had related this to the previous concept I had explained. On the basis of frame of reference, on this basis I had related this. So we can write it as velocity of b minus velocity of a. If the bodies are moving towards or away from each other, directions of VA and VB are opposite to each other. If the directions of VA and VB are opposite to each, if the direction of VA and VB are opposite to each other, then VBA is equal to VB minus minus of VA, and it can be written as VB plus VA, VB plus VA. Means if they are moving in the same direction, then this is VB, this is VA, then VBA is equal to what? VB minus VA. And if they are moving with opposite direction, then VBA is equal to VB minus minus VA, that is VB plus VA. Clear, students? I think all of you had got it and it is clear to you. Now the second example. Second example. This is Earth. This is a velocity of a point on the Earth. Velocity of point on the Earth, and it is denoted by v. And a satellite is moving in the same direction with velocity capital V. This is a small v and this is capital V. If the satellite moves from west to east in the direction of rotation of the Earth, in the direction of the rotation of the Earth axis, its velocity relative to Earth's surface velocity of satellite with respect to Earth is equal to velocity of satellite minus velocity of Earth. Velocity of satellite minus velocity of Earth. And if this velocity is in opposite direction, means if satellite moves from east to west, in the direction opposite to rotation of the Earth, its velocity of the Earth with respect to Earth is minus VE, and it is equal to Vs plus VE. Vs plus VE. This is the velocity of satellite. Now, the next thing, third example, if a train is moving at equator on the Earth's surface, a train is moving at equator on Earth's surface. VTE, velocity of train relative to Earth's surface, VE, velocity of point, velocity of point on the surface of Earth relative to its center. So there are two cases. When the train is moving along the direction of rotation of the earth, and if the train is moving opposite to the direction of rotation of the earth. Okay, first is, suppose this is earth and this is equator. This is train and this is velocity of train with respect to earth, and this is the velocity of earth. This is velocity of earth. So VTE, velocity of train with respect to earth. Since the train has the velocity in the same direction along the rotation of the earth, so it can be written as velocity of train with respect to ground minus velocity of earth with respect earth, velocity of earth. Or you can write it as velocity of train is equal to velocity of train relative to earth minus plus velocity of earth. Velocity of earth. Velocity of train with respect to ground, velocity of earth with respect to ground, or same with respect to earth, and velocity of train with respect to earth. Similarly, the case if it is like this, here don't get confused with earth and ground, because there is a frame which is common for the velocity of earth and the velocity of train, that we had supposed as ground. So not get confused with this. Velocity of train, it is opposite to the velocity of earth, and in this case and it will be earth is equal to velocity of train plus velocity of earth, and now velocity of train is equal to velocity of train relative to earth minus velocity of earth. Now students, the third case, fourth case. If a man is swimming in a river, if VMR, velocity of man relative to water, velocity of man relative to water, velocity, we have velocity of river relative to ground, and velocity of man relative to ground. So yes, first, if a man is swimming in the direction of flow of water, if man is swimming in direction of flow of water. In direction of flow of water. If man is swimming in direction of flow of water, then velocity of man with respect to river, it can be given as Vm minus Vr, or Vm can be given as velocity of man with respect to ground. Vm can be given as Vmr plus Vr. Vmr plus Vr. And if the man is swimming if man is swimming opposite to the flow of water, man is swimming opposite to the flow of water, then Vmr is equal to Vm minus Vr, and it is equal to Vm plus Vr. And from here, velocity of man with respect to ground is given as Vmr minus Vr. Clear, students? This is the case of swimming of man in a river, and numericals can be asked on the basis of this, and we will try to solve the numerical based on this. Now the next case. Next case is that a railroad car is there and a boy is running on that railroad car. The velocity of the boy relative to railroad car is called as V relative. V relative. Velocity of boy relative to railroad car. V relative. Vc. Velocity of railroad car with respect to ground, and Vd. Velocity of boy with respect to ground. Velocity of boy with respect to ground. These three velocities are given. So here also two cases arises. Case first is if the boy is running on the railroad car in the direction of railroad car. If the boy is running in the direction of the railroad car. Boy is running on the railroad car in the direction of the railroad car. So V relative is equal to velocity of car. or from here velocity of y with respect to ground can be given as velocity of y with respect to the railroad car plus velocity of car. Similarly, the second case, if the boy is running on the railroad car, if the boy is running on the railroad car, running on the railroad car in direction opposite to the railroad car, in the direction opposite to the railroad car. So here V relative can be given as VB minus of VC, or it can be written as VB plus VC, VB plus VC. And from here velocity of y with respect to ground can be given as V relative minus velocity of car, V relative minus velocity of car with respect to ground. And the last case is, that is the rain problem. We will discuss about the rain problem. Suppose rain is falling vertically downward. Rain is falling vertically downward, and this is the velocity of rain. This is the velocity of rain, and a man with umbrella in his hand moving in horizontal direction. This is the velocity of man. Umbrella. So this is the velocity of rain, and here velocity of man is in this direction. Velocity of man with respect to ground is in this direction. So negative of this is minus of Vm. From parallelogram law of vector addition, which we will study in later section, this resultant velocity of rain with respect to man, it can be given as, this angle is theta, and this can be said that velocity of rain with respect to man, Vrm, it can be given as Vr minus Vm from parallelogram law of vector addition, and the magnitude of Vrm is given. All this we will study in detail in scalar and vectors in the next chapter. Vr square plus Vm square, and the direction in which he will put the umbrella, that is theta, is equal to tan inverse. This is Vm upon Vr. This is the direction, theta is the direction in which the man must have to put the umbrella to save himself from the rain. So tan theta is what? Tan theta is equal to perpendicular upon base. The perpendicular is Vm, upon base is Vr. So tan theta is equal to Vm upon Vr. So theta is equal to tan inverse Vm upon Vr with the vertical. So this is all about the concept of relative motion, what is relative motion, and with the help of various examples, various practical examples, I had clarified you the concept of relative motion, what is relative motion, I had derived the relation for relative motion also on the basis of frame of reference, and taking the position, from the position we had derived the relative motion in terms of velocities. And I think if you will go through the complete video, then it is easier for you to make your concept clear regarding the relative motion. So that's all for today, students. In the next video we will discuss about some numericals based on relative velocity, and after that we will start the chapter 4, that is motion in a plane. Thank you, students. Have a nice day.